Hello, good evening, everyone. My name is Jamil Siddiqui, and I'll be leading you through the Calculus CRAM sessions this year. I see some chatter already going on in the chat room. That's great. If you guys could just give me some kind of indication that the volume is working well, we'll be off and running tonight. Okay, so great, excellent. So again, my name is Jamil Siddiqui. This is our first CRAM session. We're going to be doing 10 of these sessions between now and the exam, and I've got a bunch of topics lined up for you, and I'll be with you each week. Hopefully you guys will be returning, we'll know each other a little well, and then I'll be able to help you guys out in preparing for the AP exam. Kind of a strange set of circumstances we're in this year. I realize that most of us, if not all of us, are out of school at this point in time, but that's okay. Fiveable will still be here with you guys, and you'll be meeting with me at least once a week between now and the exam. So tonight our session is going to focus on limits, continuity, and differentiability. This is kind of a big topic in calculus. It's a foundational topic that a lot of the things that we do in calculus is based on. And what I want to do today is do a real quick review, because I assume that the majority of you have done the majority of you have already completed this material. But I want to talk about how is it going to be done on the exam? What kind of questions is it going to be asking? Okay, so here we go. Without any further ado, let's take a look at what we've got. Before we start, I do want to remind you that Fiveable has their weekly calendar set. Calculus is Mondays at 9 o'clock, and that's the open session, free for anyone. Our CRAM sessions will be Thursdays at 7 every week, so that's 2 opportunities you guys have for calculus every single week. On the Monday night, on April 6th, we're going to see Megan Dwyer covering the existence theorems. So that's a free one. If you guys can check that one out, it's at 9 o'clock. And as always, be following Fiveable on all of our social media, because we'll be posting updates and what's going on there and schedules. So you'll get a lot of information from that. So tonight in this stream, what we're going to do is we're going to do a brief review of limits, continuity, differentiability, and then we're going to be looking at several free response type questions that the College Board likes to have on these topics. And if you have any questions at all, put them over into the chat, and I'll do my best to get to them. And we're off and running, so let's go. Limits, we're going to start with. And first, really quick review of limits. The formal definition of a limit that we use in AP Calculus is the limit of the function as x approaches a is equal to L, which basically means we're going to get a real number output as long as we can approach from the left and the right, and those two limits agree, okay? So what I'd like to do is I'd like to start by just looking at a couple of examples and reviewing this definition with you, because we're going to see that this definition really is the basis for what where continuity comes from, as well as where differentiability comes from. So both continuity, differentiability come directly from this limit definition. So the first example I'm going to look at is a graphical example. What is the limit as x approaches 2 of f of x? I'm going to switch over to my tablet so we can work on a couple of these problems together. So if you'll bear with me while I change my screen. Here we go. Okay, so we've got our limit as x approaches 2 of our function here. Again, the idea behind the limit that I'm going to stress to you guys today, and again, it's going to play the same way in continuity and differentiability. One of the most confusing things for students when they first learn limits is they get fixated with the idea that this point is up here. And what that says to us is when we plug in the value of 2 into f of x, when we find f of 2, that's the answer we're going to get. That answer will be 2. The confusion comes for students with this because this has nothing to do with the limit. It has nothing to do with the limit at all. So what I mean by that is when we find a limit, what I suggest you do is you actually look at where you're going, in this case 2, and then actually cover it up so you can't even see what's underneath it, okay? So now, if you're trying to figure out what we're going to get as we approach from the left and approach from the right, let's imagine you're walking along this function and you're getting closer and closer to the value of 2. Well, when you get there, your assumption is going to be that the point is going to be right there where it belongs. So you're going to make the assumption that the limit as x approaches 2 from the left of this function is equal to that y value 1. And that is the correct way to take the limit. So now when we come from the other side, come from the right, we're going to be starting on the function here. We're going to be walking in this direction. And again, as you get closer and closer, you're going to make the assumption that the value of y is going to be that value 1 again. So when we look at this example, coming from the left, we get an answer of 1. Coming from the right, we get an answer of 1. If both answers agree, that means our overall limit exists, and we're going to get an answer of 1 for this overall limit. So again, if you're in a situation where you've got this hole and another point someplace else, ignore the point when you're talking about limits. It's all about where these two guys who are walking from the left and the right think they're going to end up. So the next example we want to look at, this example right here. Okay, now you can clearly see there's a jump here, there's a discontinuity. Continuity and limits are so closely related, but again, if you're answering this question and you're taking the limit as x goes to 3, what I suggest you do is you go and you cover up this value, and then you literally go on this function and you start walking from the left and the right, and you ask, as x approaches 3 from the left, what y value do you think you're going to end up at? And as he's walking, he's going to assume that his y value is right here. And that means we're going to get a y value of 3. So the answer for this limit from the left is 3. And now, when you're coming around from the other side and you're walking in from the right, this guy is going to assume that the answer to this limit is up here at 4. And from the right, we're going to give the answer 4. So we're going to have the limit as x approaches 3 from the right of f of x is equal to 4. So the way they might ask you this on the AP exam is to justify your answer, justify whether or not the limit exists. The overall limit here we're going to say is does not exist or undefined. Both answers are acceptable. And the reason we're going to say it's undefined, we're going to write out because the limit as x approaches 3 from the left of our function does not equal the limit as x approaches 3 from the right of our function. And then to show that we're really applying what we're doing, we're going to write down 3 does not equal 4 underneath. And that is going to be perfectly acceptable for the justification for this problem. And again, if I write undefined, it's the same thing as saying no limit. It's also the exact same thing as saying does not exist. All of these answers are completely acceptable. Okay. One more thing about this. Sometimes I'll have a student who will say, well, can I just write this? Can I say, hey, for this problem, the limit as x approaches a from the left does not equal the limit as x approaches a from the right? And they're saying, I'm quoting my definition of the limit, okay? This is not a good way to answer the question on the AP exam. And the reason for that is this is just writing down a definition. It's not being applied to the problem you've been given. So on the AP exam, whenever they're asking for justifications, you really want to apply the problem. So instead of writing A here, you really want to write the 3 from the left. Instead of writing A here, you want to write the 3 from the right, because that's showing that you're actually applying it to your example, and that's what they're looking for. As long as f of x is defined in the problem, you are safe using f of x. You don't have to write the explicit function, but you really should replace any of these general notations with specific parts for the problem. Okay. The next example. Before we take a look at this one, I want to switch back to my slides for just a second. So if you'll bear with me. Okay, so for this next example, before we talk about how limits are going to show up on the AP exam, what I just gave you were 2 examples of graphical limits, okay? That's when they actually give you a graph and you'll get to walk from the left and the right and actually visualize the answer. A lot of times on the AP exam, especially in the free response sections, and I don't know how much you guys have been paying attention to the changes that are coming on the exam this year, but this year the exam is going to be just free response. The multiple choice is going to be removed and you're going to be required to answer free response questions. And that's it. So the majority of questions dealing with limits this year, I tend to think might come more of an analytical way where they'll give you a function and ask you to compute a limit. And in that case, the majority of the time on the AP exam, L'Hopital's rule is the way to go. So if you're familiar with L'Hopital's rule, it says that if you apply a limit, and it's got to be in the form of a fraction, it's got to be a numerator and a denominator, function in the top, function in the bottom. And that results in any indeterminate form. And in AB calculus, the two indeterminate forms that we are most concerned with are 0 over 0 and infinity over infinity. So if you ever kind of go through the limit and you kind of just substitute in directly and you get these indeterminate forms, that is a huge, huge, huge clue that you are supposed to be using L'Hopital's rule. And what L'Hopital's rule says, when you take the limit as x approaches a of f of x over g of x, if you get an indeterminate form, try it again, but this time use the derivative. Use the derivative of the numerator over the derivative of the denominator. The number one mistake here students make is they use the quotient rule. That's not what this is saying. This is saying do the numerator separate from the denominator, and then that's what will work, okay? I've got a question over here, and it's a great question. As you try with L'Hopital's rule, you might do the derivative of the top and the bottom the first time through, and you still might get another indeterminate form. You might get 0 over 0 in that case. It's perfectly okay to continue using L'Hopital's rule over and over again. Every single time you take a limit, if you get an indeterminate form, you're allowed to do L'Hopital's rule. So you could see an example where L'Hopital's rule is repeated, and you might have to do not just the first derivative over the second derivative, and then you might have to even do a first derivative. You might do the derivative of the numerator over the derivative of the denominator. You might get an indeterminate form, and then you might do another round where you do the second derivative of the numerator over the second derivative of the denominator. As long as it's indeterminate, you keep going. So I do have an example for us to take a look at. So let me switch back over to the tablet. Here we go. I'm seeing a question over here. What would be, I think it's saying, what would be the maximum number of times the AP exam would ask you to apply it since we're under a time constraint? The maximum number of times, I have never seen on the AP exam them ask you to do it more than twice, and that's only been one time in all the years I've been working with AP. Most of the time, it is just once. That's the number of times that you're asked to do it, okay? So, in this next example, we're taking in this limit, and we're doing the limit as x goes to 0. So we're going to try direct substitution on this to begin with. When we try direct substitution, our first expression is going to be ln of 4 minus the ln of 4, which is going to give us 0, and the bottom is going to go to 0. So again, I want you guys to be prepared for the free response section this time around, because that's the way the questions are going to be given. If we're doing this on the free response, we're going to use L'Hopital's rule. We're going to end up with 0 over 0. But notice what I haven't done, okay? When I'm doing this just to do it quickly and just to get an answer, a lot of times you'll see people write this expression. You'll say equals 0 over 0 here, okay? Do not do this. Do not do this on the free response. It will lead to a loss of a point on the free response, and I'm going to explain why, okay? Eventually, we're going to get an answer to this limit. Sooner or later, this limit's going to come out, we're going to get an answer, and it's going to be, hopefully it's going to be a real number. If we work this out and we get a real number, we're saying that real number ends up being equal to this 0 over 0 through our chain of logic. For that reason, if you write your limit is equal to 0 over 0 in the free response, they're going to deduct a point from you, okay? So what's going to happen here is you do need to show that the numerator goes to 0 and the denominator goes to 0. So the way you're going to show your work on this in free response to get full credit is you're going to take and do two separate limits. You're going to show off to the side that when we take the limit of ln of x plus 4 minus ln of 4, that as x goes to 0, you're going to show that that goes to 0. So you're verifying that the numerator is going to 0. At the same time, you're going to do the limit as x goes to 0 of the denominator, and you're going to verify that that goes to 0. By doing that, you've satisfied the conditions for L'Hopital's rule. You've said that the numerator is going to 0 and the denominator is going to 0. So once you've satisfied the condition, now you can write using L'Hopital's rule, and you don't have to make that clear in your work. I just want to make it clear as we're doing this together. Using L'Hopital's rule, I'm now going to keep the limit exactly the same, but I am going to take two derivatives. I'm going to do the derivative of the numerator, and I'm going to do the derivative of the denominator. So in this case, the derivative of the numerator is the derivative of the natural log of x plus 4. Okay, and then you're going to do minus the derivative of the natural log of 4. And in the first case, when we're doing the derivative of the natural log of x plus 4, that is a chain rule because we've got an inside function and an outside function. So when we're talking about the derivative of ln of x plus 4, the way I like to tell my students to work with this is think about what you have on the outside. Who's the outside function? And in this case, the outside function, I call it ln of something. That's the notation. That's the way we describe it in my class. We just call it the ln of something. And the inside function is x plus 4. Because of that, when we do the chain rule, I always use these 3 steps. The first step of the chain rule is the derivative of our outside function, which is ln of something. Well, that's going to end up being 1 over something. And the reason and the rationale behind that would be the derivative of ln of x is 1 over x. So now the second step is to copy the inside, which is x plus 4. And then the third step of the chain rule is always take the derivative of the inside, which in this case, the derivative of the inside is going to be times 1. Okay, so that's the derivative of the first term. When you go to the second term, you're taking the derivative of ln of 4. And when you take the derivative of ln of 4, a lot of people make the mistake of saying that this is 1 over 4. Now, the way that we should really work with this is we should think of it in terms of the fact that there's no variable in this problem, okay? Since there's no variable, this is a constant. And since it's a constant, we're going to take the derivative of it as a constant. It's going to end up being 0. And then for the bottom part of this problem, we're taking the derivative of the denominator. That's fairly straightforward. This is derivative is x, and we're going to get just 1 on the bottom. So once we're here, we reapply the limit. And as we reapply the limit, we're going to get that as x goes to 0, this part right here is going to go to 1/4. And the denominator is going to stay 1. So our answer is 1/4. Now, I see a lot of discussion in the chat. I'm going to come back and address some of these questions in a minute. I'd just like to finish this question so we can see how it works out. At this point in time, we're good to go. As far as the free response section goes, all we've got to do is we've got to show that the numerator goes to 0, the denominator goes to 0. That allows us to use L'Hopital's. And then we take the derivative of the top and the bottom to get it. So I mentioned one thing earlier. If we had put that 0 over 0 here, according to our work, our limit ended up equaling 1/4, but we are also saying our limit is equal to 0 over 0. By the transitive property, what we're saying, even though we don't mean it, is that 0 over 0 is equal to 1/4. So because of that, we don't want to put that 0 over 0 there. Okay, so now to go back and answer some of the questions and great questions you guys are giving me on the side here. So one thing, some of you have recognized this problem as a definition of a derivative, okay? And you are exactly right. This is a problem that could be used from the definition of the derivative. We do have an f of x plus h minus f of x over h if we rearrange this. So I agree completely. If you recognize this problem as the derivative of ln of x at x equals 4, okay? The derivative of ln of x evaluate at x equals 4, you are 100% correct. You could do it that way. And that might be a faster way to do it if you recognize that. But the reason I'm using this example is because I want to show how L'Hopital's rule works. And the thing about L'Hopital's rule, you can use it anytime you have an indeterminate form. So if you didn't recognize this as a specific definition of a derivative problem, you're covered. L'Hopital's rule is still going to get you through the example. So it's kind of up to you guys. If you saw this and you recognized it as a definition of a derivative, you are perfectly welcome to use this method of answering this question. That's perfectly acceptable. But for my purposes today, I really wanted to make sure that everyone was reminded of how L'Hopital's rule works, and I just thought this would be a good example to kind of talk about both. So I hope that clarifies some of the questions. I think I answered this just in case I didn't. You do not have to state you're using L'Hopital's rule, but it sure makes you look good when the readers are reading your work, okay? But they will not deduct a point if you leave that off. But I always tell my students, the more you can communicate to the reader about what you're doing, the more points you're going to earn. So the things that are necessary in this problem, okay, the things that are necessary, you must have that the numerator and the denominator go to 0 if you're using L'Hopital's rule, and then you must have the correct derivative on the top and the bottom, and then that will give you the answer right here. Okay? Do I think I could do a problem using the definition of the derivative? At the end of our time today, if we have time, I would be happy to go back to that. To be perfectly honest with you, I don't think it's going to be tested on the free response. I've looked at all the AP exams they've given over the last 30 plus years. There has never been an exam where they've asked you to use the definition of the derivative in the free response section. So I can't imagine that they're going to ask it this year, especially since the exam is actually going to be shorter. It's only a 45-minute exam. But if we have time at the end, I'll be happy to show a definition of the derivative. If we don't have time in the end, I'll post one up on the chat boards on Fiveable, okay, so you guys can see it. Jessica, you're right. It's more often than not a multiple choice question as opposed to a free response. So at the end, if we have time, remind me, we'll come back to it, okay? Any other questions about L'Hopital's rule before we move on? Okay, then I'm going to switch back to our slides. So let me share my screen. Okay, so for our next example, okay, that's the one we just did. So moving next, the next thing we have to be aware of. We've talked about limits and the idea of that limit again, which you got to come from the left and you got to come from the right. Okay, so I saw you one more question about L'Hopital. So Jessica, on the test, we have to split it up, the limit of the top and the limit of the bottom. Yes, you really need to do that because that's the way you're showing that L'Hopital's rule can be used. Okay, you can't use L'Hopital's rule unless you show that the top and the bottom end up going to that, leading us to that indeterminate form. So it is critical. It is critical that you show the numerator limit separately from the denominator limit. That will cost you a point if you don't. Would there be a time when we couldn't use L'Hopital's rule and would have to find the limit by factoring? In all of my experience, every time we do a factoring or another type of algebra or trigonometric manipulation, L'Hopital's rule covers it, okay? L'Hopital's rule is really, really just the safest, fastest way to handle any of the indeterminate forms. And if you do a problem, you don't get an indeterminate form, it means you got the answer right away. So I really, really would highly recommend that you guys kind of embrace the idea of L'Hopital's rule. I believe the last 2 years, they've asked a free response question that involved L'Hopital's rule, so they seem to be testing it fairly frequently, okay? I'm going to switch our attention to continuous now. Keep asking questions, though, and I'll answer as they come up. Continuity, very, very similar to the idea of a limit. Matter of fact, if you look at our definition of continuity, the first two pieces are identical. So in other words, you don't have continuity unless your limit works first, okay? There's just that third piece that we have to worry about, and that third piece says f of a has to equal your two limits, okay? So to make sure that you guys really, really get that, to make sure that's 100% clear, what I want to do is I want to take a look at one of our examples that we already saw. So let's just back up a second. So let me switch back over to my tablet. There's a question, are continuity and differentiability the same thing? They are not. Continuity is a requirement for differentiability, but there's one extra step to differentiability, which we're going to talk about before the evening's over. So I want to just jump back up to this guy right here, because this is the best example we can look at to keep straight the idea of continuity versus limits, okay? So if you remember this example, when we covered this up, we had no idea where the actual y value was. So our limit in this problem ended up being 1. That is fine for limits, okay? But when you talk about continuity, you've got to peek under that black line and see what's really happening. So when we look underneath that, we can see it's not continuous. And the reason for this is because this guy is my limit as x approaches 2 from the left. This guy is my limit as x approaches 2 from the right. But this guy up here is my f of a. Okay, in other words, f of 2 in this case. Okay, you will get the left side and you will get the right side to agree, but you will have a gap where f of a is. And that's what continuity is all about. It's about first making sure you have a limit, but then second, making sure that when you go to find the actual y value, it's where it belongs. In other words, it doesn't create a hole in your function. So that's the whole idea of continuity. So we're going to switch back. I want to show you a couple more slides, and then we're going to go and do a couple examples of continuity. So okay, so now when you're dealing with continuity, like we've got up on the screen, you know you've got to check your limit from the left, you've got to check your limit from the right, and then you've got to make sure that the actual function value is there. So in my world, what I like to do is I like to think that most functions are going to be continuous. So instead of assuming they're not continuous, I like to assume they are, and then find out what could stop it from being continuous. Okay. I see the question go back. If f of 2 equals 1 in that previous example, would it be continuous? Yes, that's exactly right. Okay. We move it into that. There's a question asking about in the free responses, do they have to state the function is continuous or not? We'll talk about that in just a minute when we talk about free response questions. So the next thing, we're back on continuity. What prevents functions from being continuous? So that's what I want to look at. Okay. So in other words, what would stop from these three things from being equal? What could prevent one of these equal signs from not working? And the first thing is if you have a domain issue. If you have a domain issue, you automatically lose continuity. If your function does not exist, you can't have f of a. If you can't have f of a, you can't satisfy this definition. So be on the lookout for domain issues on every problem, even if the problem is not about domain. Just kind of look at it. And when you're thinking about domain, the easiest thing to think about, the three ways that you can have a problem with domain, you could be dividing by 0, you could be doing the even root of a negative number, or you could have the logarithm of a number less than or equal to 0. Those are the three domain traps in calculus. So as long as you're avoiding those three things, you will be safe as far as domain goes. But there is one other thing. Oh, can I repeat that? Of course. The three domain issues, again, dividing by 0. So if you have a 0 in the denominator, all right, taking the even root of a negative number. So if you end up with the square root of a negative or the fourth root of a negative, that's going to cause you to have an imaginary number, not going to work for the domain. Okay. And then the last domain issue is when you're dealing with logarithms, you got to make sure that you don't take the logarithm of a number that is less than or equal to 0. So logarithms of negative numbers are no good. Logarithms of 0 are no good. And those are the three places you can get into trouble with your domain. That's going to cause your f of a to fail. So that's kind of the last equal sign. The first equal sign will fail if the limit from the left and the limit from the right don't agree. Now, in my experience, there's really only one way that can happen. The only thing that can cause your limit from the left to be different than your limit from the right is if you have a piecewise function. So piecewise functions are really, 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 really something you have to be aware of when you're talking about limits, when you're talking about continuity, when you're talking about differentiability, because they're the functions that the left side and the right side can disagree, because you might have one function on the left and a completely different function on the right, and they're not going to match up. So the AP exam, like I said, they love to talk about piecewise functions. So here's what I'd like you guys to do for a moment. Okay, I'm just going to give you like maybe 3 minutes. There's a question here. It's a piecewise function, and the question is f of x continuous at x equals 2? Can you justify your work? So I'm just going to give you like 3 minutes to give some thought on this, and I'm going to check back with you in 3 minutes, and then we'll go and read through some of these questions and make sure I'm answering everything you guys are asking me. So take about 3 minutes, and then we'll come back and we'll check this answer out, okay? If you, I'm sorry, we'll just check it out in about 3 minutes. All right, I'm seeing some good answers coming up on the side. We're going to take a look at this problem just to make sure that you're writing it correctly, to make sure you earn all the credit on the AP exam. So I'll switch over to my tablet. So here is the example we're looking at, and a lot of you guys have gotten the correct answer. But again, on the free response section, it's not enough to have the correct answer. You've got to make sure you show the work as well. Okay. So in this problem, what I tell my students is, all right, we're going to go and we're going to find what we consider to be the key word in this problem. And I'm going to hang my hat on this word continuous right here as being the most important word here. And whenever I hear continuous, I'm thinking, hey, does the limit as x approaches a from the left equal the limit as x approaches a from the right equal f of a? Okay. Now, you don't have to write that to earn credit, but you have to apply it to earn credit. So what we're going to do to earn credit on this is we're going to take each of these three parts and make sure we show the work that goes with it. So the first thing we're going to do is we're going to take the limit as x approaches. Our a value here is 2. So we're going to go 2 from the left. And now you just got to be careful and make sure you pick the right function, okay? In a piecewise function, what we've got is two pieces defined on different intervals. Very, very careful. You got to read what's going on here. This is saying use the top expression whenever x is less than or equal to 2. So as we approach 2 from the left, that means the value is less than 2. We have to use the top expression. We've got to use the x squared plus 3x in this expression, okay? So that's the first piece of the puzzle. We're going to have to find this limit. Now, the second piece of this puzzle, we now have to find the limit as x approaches 2 from the right. Well, again, looking up here, this says use the bottom anytime x is greater than 2 or on the right side of 2. So we're going to use 3 times the square root of x plus 14. So now we've set up our two expressions. We are on the way to getting our credit. All we've got to do now is check out what's going on with these two guys. And then lastly, before I forget, we also have to make sure we make a determination of f of a. Now, some of you guys are going to feel like this is kind of redundant because we've already going to kind of talk about this. But because the definition clearly says there are three parts, we want to demonstrate all three parts, okay? We want to demonstrate it. So I want to make sure that when we find f of a, I'm using the right expression. F of a is really f of 2. F of 2 is going to come from the top one because of the equal sign right here. So that's where we're going to plug into. So to find f of 2, I'm going to do f of, my input is equal to that thing squared plus 3 times that thing. And then I'm going to have to show 2 for this. All right. Now, I know a lot of people are starting to ask, hey, do I need to show this all the time? What if we prove it just using the first two? I agree. If we disprove it after the first two, we don't have to show this, okay? But I like to just show the entire process to make sure everyone's good. So we'll comment on that kind of towards the end. When we take the limit of this, we're going to do this first limit by substitution. We're going to plug 2 in for both of those guys. So we're going to get 4 plus 6, which is going to give us 10. And then when we do the substitution in the next one, we're going to get 2 plus 14, which is going to give 16. Square root of 16 is 4, and then 4 times 3 is 12. So some of you guys have already commented, we know this is a continuous already, and I agree. We don't have to go any further in the proof of this. So we could leave this part out for this particular example because we've already shown that these aren't continuous. So now to answer the question, you always want to make sure you answer what you're being asked. If you just left this, we're not getting credit. They asked, is this function continuous? We have to say f of x is not continuous at x equals 2. And if you had this, you'd be fine. A lot of times they'll throw in that word justify in there. And if it's a free response question, they actually will, okay? So if we throw that word justify in there, we can't just stop by answering it. We now have to give the reason we gave this answer. And the reason we gave this answer is because the limit of f of x as x approached 2 from the left did not equal the limit of f of x as x approached 2 from the right. I would go one step further. You don't necessarily have to, but I would go one step further, and underneath it, I would make sure they understand it's because I found 10 for one and I found 12 for the other. Okay, so this would be a perfectly good justification for this problem. I'm just reading over the questions real quick. Would they ever give a trick question without one piece of info where you would have to? No, they're not going to do that. They're always going to give you enough information. So there's never going to be a trick question like that. Okay. So I think that's good over on the side there. To me, this is your answer. This is what you're going to want to show. If you show all of this work with the justify prompt, you're good. Okay, you're good. Now, just for argument's sake, okay, just for the sake of argument, had this answer turned out to be 12, okay, had it turned out to be 12, you would definitely have to go and show the third part, because you'd have to show that there's still a chance that all three parts could match. Okay, so when you prove continuity to be true, you need all three parts. When you disprove continuity, just one part failing means you've disproved it. I've heard that's always good to include a one-sentence explanation explaining what you did. The only time that's necessary is if it says justify, or if it says to interpret, or if it says to explain, or if it asks you why, any of those things. If they had just asked this question, is f continuous at x equals 2, it would have been a free multiple choice question, to be honest with you. In the free response section, they would have always asked justify with this problem. Okay, so I hope that makes sense for everybody. I'm going to give you a couple minutes. I'd like you to try this. It's a twist on the continuity question. Again, another type of question that I've seen in the free response. So if you guys take a moment and try this, we'll come back in about 2 or 3 minutes and see how you did. This example is a twist on the last example, okay? In this problem, we're still looking at this. We are still seeing this word continuous down here. And as long as the word is continuous, we are talking about that definition where the left limit has to equal the right limit, has to equal the function. So if I just go straight to that definition and I do the limit as x approaches, well, here's the deal. Whenever you've got a piecewise function in these problems, the place where you are most interested in looking, okay, the place where you're always going to be looking is at what I call the crossover point, because that's where the left side and the right side have the ability to disagree. That's why piecewise functions are so tested in these topics. So we're going to take the limit as x goes to 3 from the left. Again, which function do we use? Well, we use the top one because that's where we're on the left side of 3. So we're going to do cosine pi x. Then we're going to take the limit as x approaches 3 from the right. And we're going to use the bottom function because that's when we're greater than 3 on the right side. So we're going to get x squared plus kx minus 2. And because this one isn't a justify, the f of 3 question really doesn't need to be done, but I'm going to put it there just to be complete. When we take that first limit of cosine pi x as x goes to 3, okay, that's by substitution. We're really talking about the cosine of 3 pi. The cosine of 3 pi ends up being -1. When we take the limit of the next one by substitution, we're going to get that this is equal to 9 plus 3k minus 2 by direct substitution. Okay, so That means 9 plus 3k minus 2 is the limit from the right. -1 is the limit from the left. We now have to set these two things equal. And the reason we do that is because it says we are going to make it continuous. And if we're making it continuous, then the left and the right have to be the same. So we're going to clean this up a little bit. We're going to get -1 equals, we're going to get 7 plus 3k over here. Then we're going to subtract 7 from both sides. And now we're going to divide both sides by 3. And several of you guys on the side in the chat have gotten this already. We are going to get a k value of -8/3. Okay, -8/3. So this is the way we're going to handle continuity in this particular example. I hope that makes sense. I hope everyone's good with the ideas of continuity right now. Okay. How do we get -1 for the limit on the left? The limit on the left, this guy right here, we're talking about the cosine. I'm doing direct substitution now. It's going to be the cosine of 3 pi. Okay, so the cosine of 3 pi is the same as going all the way around the circle once and then going another pi. So, some of you guys are saying unit circle. That's one way of looking at it. I like thinking about it by looking at the graph. If we think about the graph of cosine, we know between 0 and 2 pi, that's the graph of cosine. So if I'm looking for the cosine of 2 pi, well, this is 1 pi right here. This is 2 pi right here. We're going to continue again and retrace to get to here. And that means this is going to be the same answer for 3 pi. Okay. So I hope that makes sense for everybody. We're now going to switch back and we're going to talk about the idea of differentiability. So let me switch back to my slides. And all right. Okay. So now as we look at the slides, the next question, or the next thing we're going to go to is differentiability. So we answered the continuity question, and now we're going to talk about differentiability really quickly, okay? So differentiability is when, first of all, you've got to be continuous. So everything we just went over has to be in place. If you're not continuous, you're automatically not differentiable. Matter of fact, let's just talk about the word differentiable for a second, okay? The ending of the word differentiable is able. It's able. It means you're able to do something. And the beginning of the word differentiable is that prefix diff, D-I-F-F. Same thing as different. If you're thinking about things that are different, it means they can change. In calculus, if you can change, it means you have a slope. And if you have a slope, you've got a derivative. So the word differentiable literally means you are able to have a derivative. That's what we're talking about when we talk about differentiability. We're able to have a derivative, which means we're able to have the slope of a line that's tangent to our curve at that one point. So for that to happen, first and foremost, you've got to be continuous. If you're not continuous, you're out of the game already, okay? After you've established you're continuous, for you to be differentiable, all you've got to do is think about the derivatives, the slope of the function. So for you to be differentiable, the slope coming from the left has to agree with the slope coming from the right, okay? So if the slopes coming from the left and the right agree, you're going to be differentiable. So I'm going to switch over my tab. I'm going to look at a couple of different drawings to make you really understand this. Here we go. Oh, sorry. There we go. And switching back. Okay. So here is a graph that we're looking at, and we ask, is this thing differentiable? Okay. Well, first of all, is it continuous? You got to figure out if it's continuous first. Now, visually, you look at this, you can see this thing is connected everywhere. So we've satisfied continuity. Everywhere on this graph, the limit from the left is going to equal the limit from the right. But what most people notice about this graph right away is they notice this value here and this value here. Because what we've got are, and Jessica, you've got these sharp turns, okay? Sharp turns are the enemy of differentiability. If you've got a sharp turn, you do not want to be asked about differentiability because it's going to fail. Some places we call this a corner. Some places we call this a cusp. It really doesn't matter what you call it on the AP exam as long as you say it's not differentiable. And the way I think about this, again, if I'm walking in this direction and I'm walking in this direction, okay, they will meet at 4. So that's the continuity part, okay? The limit exists. They're going to be there. The f of a value is going to work. So they're going to meet. We're continuous. But what's going to happen is these guys get closer and closer and closer. Is my guy on the left is looking in one direction, and my guy on the right is looking in a different direction. And what that means is they're going to just crash into each other because they're not going to see each other coming. And because their slopes don't agree, we can't say that there's a single tangent line at that value. There is no single tangent line. So again, just to draw this out, if I'm coming from the left, my tangent line is going in this direction. And if I'm coming from the right, my tangent line is going in this direction. And because they're going in two different directions, this is not differentiable. Okay, this is not differentiable. So where's the other place on this graph where we're going to have a point that's not differentiable? Well, I think you're all going to see it. The other place where this graph is not going to be differentiable is when x equals, excuse me, exactly, at x equals 7. Same reason. Coming from the left, our slope is going to go in this direction. Coming from the right, our slope is going to go in that direction. And that makes for a point that is not differentiable, okay? Just to kind of contrast this to what I like to call a smooth curve. If we have a smooth curve and we talk about going to that value, well, if I come from the left, that's the direction I'm going in, okay? And if I come from the right, I'm going in the same direction. Because I'm going in the same direction, this is perfectly okay. This is differentiable. So again, this is kind of, in my class, we call it smooth. If it's smooth, you're going to be differentiable. You guys said it was a sharp turn. You're absolutely right. These cusps, these corners, these sharp turns, whatever you want to call them, that is what's going to cause all sorts of problems when you're trying to find differentiability. Okay? I'm just looking at the questions here real quick. Is the differentiable point defined by the x value to tell where it lies, or the xy to identify exactly where it is? The majority of times on the AP exam, they ask you for the x value where it is not differentiable. So the majority of the time, they're asking for the x value, but always read the question, read it carefully, make sure you answer. If they ask you for the point, they want the x and the y, you'll give it to them. But the majority of questions, it's the x value. I've got a question. How does a cusp look? It all depends. I've seen different books, different people use the word cusp to represent what we have in this drawing, having these corners, okay? Some people say a cusp is only when we have a vertical slope like this, okay? So if you look at this guy right here, this guy, as we take the slope going from the left and the right, that slope is becoming vertical, okay? So if it's vertical, the slope there will be undefined. So you could actually see a slope like that right there. So on the one hand, you can kind of say, well, it has a slope, but on the other hand, you're saying, yeah, but the slope is undefined, okay? As far as the exact definition of a cusp, not going to be important. The AP exam acknowledges that different teachers call different things cusps, so it's not really going to come into play on the AP exam, okay? What's important is that you understand a sharp change. That's what it is, okay? If they say the value, do you have to specify the value, or do you assume the x? They will make it crystal clear. They will say x coordinate. They will make sure there's no ambiguity on that. Okay. So for the next problem, what I'd like to do is I'd like to take a look at this example. Okay. So again, we've got this idea of a piecewise function, and the idea is to find out, is this function differentiable at x equals, if it's differentiable, what do the values of a and m have to be in this function? Okay, so again, I'm just going to give you a second to think about this, not a whole lot of time, but maybe a minute so you can get your brains working on this, and then we're going to discuss it together, okay? Okay, so in the interest of time, we're going to start taking a look at this one. And I wrote a note over there in the corner that I want to make sure you're all super clear with. You can't talk about differentiability until you talk about continuity first. So the very first thing that needs to be done in this problem is you've got to do your continuity. You've got to take a look at x approaching 0 from the left, and you got to take a look at x approaching 0 from the right. So in this example, the top expression is coming from the left, the bottom expression is coming from the right. So as you look at these, you're going to get for the coming from the left, when you use 0 by substitution, the natural log of, it's going to be 0 plus 1, which is the natural log of 1. Natural log of 1 is 0. So this ends up being a plus 0, which is just a. In the second example, anything that has an x as a factor is going to disappear. So we're going to lose the negative m, and we're going to end up with m plus 3. So what we learned from the first expression is that a has to equal m plus 3 for this to be continuous. Okay, so that's what we learned. It's not our final answer, but it's a start. Okay, how did I get m plus 3? I'm doing direct substitution with x equals 0. So as soon as x equals 0, we lose this first term, but m plus 3 stays. Okay, so there is our result from continuity. Now we've got to take our result from differentiability. Now, in order to do that correctly, we got to know the derivatives. We got to know the derivative coming from the left, and we got to know the derivative coming from the right. So over on the side here, I'm going to take the derivative of each expression. So I'm going to start with the bottom one, because the derivative of negative mx plus m plus 3. M and 3 are constants, so we're going to lose those. And the derivative of negative mx is just going to be negative m. So that's the derivative for this guy. On the top, a again is a constant, so we're going to lose that. Well, it's going to turn to 0 when we take the derivative. And now we're just taking the derivative of the natural log. Earlier today, I talked about the chain rule for natural log, and that's what we're going to use here. So it's going to be 1 over. We're going to copy that ax plus 1 for the inside, and then we're going to take the derivative of the inside, which when we take the derivative of that 1, it's going to go to 0, and the derivative of ax is going to be just a. So we're really going to end up with this guy, and then I'm just going to write an a in the numerator. So that's the derivative from the left and from the right. So when I come down below and I do my differentiable piece of this puzzle, I've got to look at what the slope is coming from the left. And again, from the left, when x is less than 0, we're using a over ax plus 1. And now we've got to take the limit as x approaches 0 from the right. And this time we're using when x is greater than 0, the expression there. And that's just going to be negative m. Which means when we take these limits, we're going to get, for the first one, we're going to get a for our answer. And for our second one, we're going to get negative m. So now we have an equation that says a equals negative m. That's our second piece of information. Now, you may notice they have given me two unknowns in this problem. They've given me a and they've given me m. So now what we need to do is, because there are two unknowns, we've got to solve a system of equations. So the bottom ones here is pretty nice. We know what a is equal to. So everywhere we see a in the top equation, we're going to replace it with negative m. And what we're going to get is negative m equals m plus 3. Solving this for m, we're going to get 0 equals 2m plus 3. And then we're going to get negative 3 equals 2m. And then we're going to get negative 3 over 2 equals m. At that point in time, we know that a is equal to the negative version of m. So we're going to end up with a is equal to positive 3/2. And those are the values of a and m that we're looking for. Okay. I see some questions in the chat. Is everyone okay? I see you kind of answered it. That's the last part of the chain rule, the denominator. When you do the chain rule, the first two parts of the chain rule, I think we all agree is this, right? Everybody agrees that's the first two parts of the chain rule. The third part of the chain rule is you take that entire first two steps and you multiply it by the derivative of the inside. The derivative of the inside here is just a, okay? So you don't pick up where you left off in step 2. You continue with a brand new factor. Okay, so I hope that answers your question. Is everybody okay with that now? All right, so next, we're going to switch back to the slides. We're going to do a couple more things. Okay, so our next set of slides. Here's what I want to point out. Differentiability is not always a main concept being tested on the AP exam, but it plays a background role on lots of different questions, okay? So I want to show you the next slide. Here's an example that is a pretty common example on the AP exam. They give you the graph of a derivative, and then part A is not directly related. In this one, if we'd had more time, I was going to work out part A, but we're running a little short on time, so I'm not going to do that with you guys tonight. But part B is the part I want to talk about. You're given the graph of f prime, and they're asking you to find f double prime of 1 and then f double prime of 4. Okay, so in this case, and I'm just going to switch back to my tablet for the rest of the evening. In this case, when you're looking at that, what you're really being asked to do is to think about the slope of f prime, because that's what f double prime is. So again, I'm focusing on part B here, and I'm looking at f double prime of 1 and f double prime of 4. If you think about this, f double prime of x is another way of saying the slope of f prime of x, because the word slope means derivative. So in these pictures, what I tell my students to do is translate f double prime to the slope of f prime. And then, because of this statement right here, they gave us the graph of f prime. We can now say this is the slope of, and don't say f prime, say the graph instead. So now, when they ask us for f prime, double prime of 1, what they're really asking us for is the slope of the graph at x equals 1. So in this problem, you come up here, you're like, okay, x equals 1 is right there. So I'm talking about the slope of the graph that follows that direction right there. So all we've got to do, all we've got to do is find the rise over the run of that particular segment. Once you find the rise over the run of this segment, you know what the slope is there, okay? So the run of this guy appears to be 6, and the rise appears that it's going down 3. So that would be -3 over 6, or -1/2 in this case. But it's the second part. Find f double prime of 4. Well, that's the slope of this graph at 4. Well, if you go up here and you look at 4, now you're talking about the slope of the graph right there. And what do we see? We see a sharp turning point. We see the idea of a corner or a cusp. So automatically what we do on this one is when we're asked this question, we say that this is undefined, okay? The value does not exist because the second derivative is the derivative of the derivative, which means it's the slope of this graph, and this is a point that is not differentiable, okay? So I hope that makes sense for everybody. Here we go. I'm going to go back and wrap up with a couple more of my slides. We're going to go a little over, so I hope that's okay. Okay, so just to wrap up, a couple of other things you should be aware about on the AP exam. Okay, a lot of problems start off, and this was one of the questions I saw earlier today. Okay, a lot of the problems start off by saying let f be a function that's differentiable for all real numbers, or let f be a function that's twice differentiable for all real numbers, or so and so have continuous second derivatives. This is all ways of saying your function doesn't have a cusp, or your function is continuous. If it says it's differentiable, then you know it's continuous automatically. So why is this so important to start in the STEM? And I'm going to give you a real big hint. If you see any example start with any of this information, it means we're allowed to use our theorems. Okay, now there was a question on the side about the theorems. I believe Monday on Fiveable is our our next stream that's free to everyone. They're going to be talking about the theorems during that stream. So I'm not going to get into a lot of detail other than just to give you a little introduction. All of these theorems need continuity to work. If you don't know your function is continuous, you cannot use these functions, these theorems. So it is imperative that when you're trying to use any of these theorems, you first have to say that it's continuous. And if it's the mean value theorem, which is the one that's used the most often, one step further, you've also got to say that you need differentiability. So you've got to make sure that the problem states these things, and that's where all of these cues come in. If you see any of this stuff, then that is important to make sure you can use your theorems, okay? So I do want to just say one more thing. I had a question. We're running a little short on time. You guys will see this when I post the slides from this. We'll give you a chance to go over it. But in both cases here, you're going to end up using one of our theorems. When you answer this on the AP exam, if you say, like for instance, in example A here, you're going to show this is true by the intermediate value theorem, okay? But you can't just say, yes, it's true because of the intermediate value theorem. If you're going to say the intermediate value theorem in the response, you must first state that the function is continuous, because you can't use the theorem without stating the condition. So in that explanation, it should start off, because my function, in this case, h of x is continuous, the intermediate value theorem applies, and then you show the work of the intermediate value theorem. In part B on this one, just to give you a heads up, if you guys try this on your own, this is going to use the mean value theorem. So to use the mean value theorem, you're going to have to state that the function is differentiable first. So the first line of your explanation should be, since this function h is differentiable, the mean value theorem applies, and then you show the work of the mean value theorem, and that would get you the full credit for this. Okay, so I apologize for rushing through that a little bit at the end, but there will be a follow-up stream next week on the existence theorems. So just to wrap up, thank you for coming tonight. This was our first session on the AP CRAM for AP Calculus. We're going to be doing this again next Thursday night at 7 o'clock. Our next two units that we've got in store for you are a unit on practicing finding derivatives, so you'll be able to find the derivative of anything. I know there are a couple questions tonight about making sure we can compute derivatives correctly. And then 2 weeks from tonight, we're going to be coming back with related rates, okay? So I'll take a second and just look at the questions here real quick. Would you have to show the work showing that the function is continuous or differentiable? On that last example, because it's stated that f and g are differentiable in the stem, it is given that any combination of f and g will continue to be differentiable. So you'll be all set. I will be sharing the slides on the Fiveable website a little bit later this evening, so you will be able to access these slides later on this evening. And I apologize for not having them ready for you in the beginning, okay? Any other questions from you guys? We are going to be working together for the next several weeks. You guys have decided to go with the CRAM sessions, so you have access to me once a week to start, and then as the exam gets closer, we're going to be doing multiple sessions a week. And I can tell some of you guys have been following along tonight. Trevor Packer announced some of the new dates. So I will be looking at those dates and planning our sessions accordingly. Hopefully we will not need a cry session. I hope we'll be all right. Okay. So what I'd like you guys to do right now, just if you have any inputs or any feedback on how this evening went, if you could just give me some comments. I'll take your comments seriously. I'll be working with you guys the rest of the way. So if there's something you'd like me to do differently, or if there's other things you'd like me to go over, or if you're happy with the way things work tonight, please give me a couple of comments. And as we work together between now and that AP exam, I will be looking at those and tailoring these lessons to help you guys out with whatever you need. So I'll just leave the chat open for a few minutes in case anybody has any comments or questions. I saw this come up earlier, so I'll share this because some of you guys are in BC Calculus. BC Calculus has gotten rid of some of the topics. Some of the topics, because of the way they've shortened the year, because of the coronavirus, polar coordinates and parametric equations will not be on the BC Calculus exam anymore, okay? They will not be on the BC Calculus exam. Sequences and series, only some series will be on that, okay? There will only be some series. So be watching Fiveable and paying attention to our streams. As of right now, we don't have a date set for that, but now that we know when the exams are, we'll put that together, okay? So any other questions or comments? Again, any feedback on how this evening went, greatly appreciated. I'll stay here for a couple more minutes just to answer any other questions that come up. But if you're all set, have a great night, and thank you for joining us. Yes, the sessions we do on the CRAM will only be material that is directly on the AP exam. Okay, so if you're coming to a CRAM session, it is strictly preparing you for the exams that you will see this year. Thank you guys for your comments. I appreciate it. If you like it, we'll keep doing the same thing every time we meet. As far as the BC exam goes, the BC exam, obviously everything that's on the AB exam is also going to be on the BC exam. So we need to talk a little more at Fiveable and find out what we're going to do in terms of BC specific stuff. So be paying attention. There will be announcements going out, and we'll follow up with that. Okay. And again, I will post the slides tonight, and the next time we meet, I'll have them ready for you ahead of time. Next week, our CRAM session is specifically on making sure everyone is comfortable with derivatives. Okay, so that is one thing that we will be doing for next week. Feel free to tune in, and I will be happy to take you through all the derivative work. All right. If no one else has any comments or any questions, thank you very much. I hope you enjoyed it. I hope it was good to help you get prepared. Now let's start getting ready, and we'll meet again next week. And I look forward to working with you guys again. You've been a great group. Thanks for all the feedback. Thanks for all the answers on the side. Looking forward to seeing you next week. Have a great night, everybody. Those are still out there. I just looked at the questions and answer. Are these sessions recorded? They are recorded. All of you guys with the CRAM pass will have access to them and the recordings. As far as downloading goes, I do not believe you can download them, but you can log into Fiveable from wherever you are, and you'll have access to them online. All right, everybody. That's it for me tonight. Everybody have a great night. Thank you for coming.